Hi everyone, welcome to the Altitude STEM Club YouTube channel. Understanding scientific phenomena by doing experiment is my passion. Today we are going to repeat the experiment which was done by Oersted in 1820. He discovered that a current carrying conductor has a magnetic field. I have already done this experiment in my previous video. Those who haven't watched that video, please visit the first part and see that video. In that video, I was using a magnetic compass and a current carrying conductor. The magnetic compass which was used in that experiment was this small magnetic compass. So the deflection was not very clearly visible in my experiment. So today I am going to do the experiment once again with proper setup and with variation in the setting of the experiment. For doing that experiment, we need two materials. One is a magnetic compass and other is a current carrying conductor. So we need two things. So let me use this magnetic compass. I can remove this magnetic needle and I am going to use this setup for passing the current through this copper wire. According to my position, this side is north and this side is south. Currently, there is no magnetic field in this area. So it is pointing to the geographical north and this side is pointing to the geographical south. First, let us understand what are the various parameters or different setup that we are going to do today. This is the first setup which I'm going to do. The magnetic needle is below the current carrying conductor and it is aligned with the current carrying conductor. We can change the direction of the current either from this direction to this direction or from this direction to this direction. And another setup, another experiment will be, we are going to keep this needle above the current carrying conductor and let us see the deflection of the needle. According to Hans Christian Ørsted, the direction of the magnetic field is given by the right hand's thumb rule. Without doing this experiment, we should be able to determine the direction of deflection. If you want to do that, please pause the video at this point and try to find the direction of the magnetic compass needle deflection before doing this experiment. Try to find it out and see whether your understanding or the answer that you have got is same as what we got as an experiment output. If you want to know how to find out the deflection, in my previous video I have given the explanation how to find the direction of the deflection. So first let us do the experiment. I will connect, or I will let the current to pass through from this direction to this direction. So it means that this is the way how we have to find the direction of the magnetic field. So let me connect this one here and let me connect the negative on this side. So if I connect this one, so the magnetic needle deflects on this direction. The magnetic needle deflects on this direction. Let us try to understand that with the right hand thumb's rule. In my previous video, I have explained that this portion we can consider as a north pole, because if you see the magnetic lines of force or magnetic field is a vector quantity. If you see a bar magnet, The magnetic lines of force or magnetic field originate from the north pole and then terminates towards the south. And inside the magnet, it is from south to north. It means that outside the magnet, it is from north to south, and inside it is south to north. With that understanding, I am considering, when I do like this, when I use the right hand thumbs rule, I consider this tip as a north pole. So when I do like this, the north pole of this and the north pole of this magnet, so it experiences a repulsive force because the like pole repels its other. The magnetic field develop is not only at a particular point, it develops for this whole length of the wire. That is why this magnetic compass needle experience a force at each and every point throughout its whole length. So it experiences here, 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 here. But when we try to understand at the tip of this south pole, then this is north, this is south, so it experiences a force of attraction, whereas it experiences a force of repulsion on this side, because like poles repel each other and like poles attract each other. Therefore, the two forces which are opposite in direction, and it has a pivoted point here, therefore it experiences a couple, it experiences a torque which tries to rotate this in this direction. Because we have a pivoted point here, therefore the torque on this side and the torque on this side tends to rotate this magnetic needle in this direction. Now, let me repeat for your observation. Let me repeat once again so it deflects. So this is the first part. Now, if I keep the magnetic needle, above the wire, then what will be the deflection? So let us see that part. So I will be using this wooden block so that it's little higher, or if I use this one, no, let me use this one, this is little higher. So let us see, it should be exactly, yeah, so fine. Let's make it stable. Now still I am not changing the direction of the current. Still the direction of the current is from this direction to this direction, but the changes in the setup is we are keeping the magnetic needle above the current carrying conductor and is in the same line. So let me connect this one. In the previous case, it was deflected in this way, and let us see in this scenario in which direction the magnetic compass deflect. Let us see. So when I connect it, we observe that the magnetic compass needle deflect in this direction, which is opposite to the direction of the first setup. Now let us try to understand this deflection also with the help of the right hand thumbs rule. So if I do like this, so I will curl my finger in this way. So when I come with, when my finger curls, it experience the north and experience the magnetic field developed by the current carrying conductor north. So there is a repulsive force between these two. But when I go at this side, this is a north and this is a south, there is a force of attraction. So in this case also, there is a repulsive force experienced by this on this side, and the attractive force on this side. Because of that, two forces, one is on this direction and one is on this direction, which are opposite to each other, and it has a pivoted point, and the two line of force are separated by a distance. That is why it experiences a rotational motion. So the torque on this direction and the torque on this direction makes the compass needle to rotate or deflect in this way. Let me repeat once again. So let me hold it this one. So now it is deflected in this direction. I release it, and then let me do once again. So it deflects on this direction. So it is given by the right hand thumbs rule. So you have to curl your finger around this wear. That is why it deflects in this direction. Now, if we change the direction of the current, what will be the direction of the deflection? So let us see that one also. So I will change the direction of the current. Now, in this case, I have to hold it like this. So let me pass the current. Now we are passing the current from this direction to this direction. So let me pass the current. So if I pass the current here, when I pass the current, the deflection is opposite. Before it was deflecting in this way, now it is deflecting in this way. So it is deflecting in this way, in this direction. Before it was deflecting in this direction. So we should try to understand the same concept applies here also, the right hand thumbs rule. So we consider all this as a north pole of the magnetic field produced by the current carrying conductor. Now let us remove this one. If we remove this one, in the first experiment, it was deflected in this way. Since we have changed the direction of the current, it should deflect in this way. Let us see. Now it deflects. It deflects in this way. So these are the changes in the parameter or different way to perform the experiment. So let me do once again. So it moves in this direction. Now let us try to do one more experiment. Say, okay, if a current carrying conductor, if we have a current carrying conductor, there is a magnetic field around the current carrying conductor. Then if I move away from this current carrying conductor, what happens to the magnetic field? Does it increase or does it decrease? In this experiment, we are not changing the amount of current flowing through this copper wire. We can do that experiment also, but right now I don't have the proper setup, but I cannot give you the exact numerical figure. But let me reduce the current and let us see how much. So I have reduced the current a lot. It's almost negligible. Yes, it deflects. Now let me increase the current. Now let us see how much deflection that we can see. But I cannot give you the correct numerical figure how much current is passing through this wire. So now I have increased the voltage supply. So obviously the current will increase. So let us see. Now when I connect it at this time, the amount of deflection is more. It means that the magnetic field developed around the current carrying conductor is directly proportional to the current passing through this conductor. Now, the other setup, we have kept the magnetic needle in line or in parallel with the current carrying conductor. What will happen if we make it 90 degree? What will be the deflection of this magnetic needle? Let us do this experiment also. Let us see in which direction the magnetic compass needle deflect. So we will do for both below the current carrying conductor and above the current carrying conductor. Let us pass the current from this direction to this direction. So let me connect the positive terminal on this direction and let me touch here and let us see. I have passed the current, but there is no any changes or there is no deflection in the magnetic needle. Let me do once again. I have passed the current, but I don't see any deflection. What may be the reason or why the needle is not deflected when we pass the current? What may be the reason? This is what we are going to find out. Now, let us do the experiment by keeping above also. Let us do that experiment. Let us give this needle above the current carrying conductor. Let us see. I pass the current here. Still, I'm not able to see any deflection. First thing, when we do an experiment, we should understand what are the parameters that are involved in performing the experiment. The first thing, our compass or our needle, which we are using in our experiment, can rotate only in this plane. Second thing, it can have a deep in the magnetic compass up to certain angle, but it cannot rotate in this, doesn't have an option to rotate in this direction, but it can has a small angle deep but not a complete rotation. So why, when we keep the magnetic compass in this setup, why it is not deflected? We know that the current carrying conductor has a magnetic field and it's governed by the right hand thumbs rule. The direction of the magnetic field is given by the right hand thumbs rule. So the current is flowing from this direction to this direction. So it is like this. Even though when you do like this is not, so it should move, but it is not moving because the force experienced by this magnetic compass needle is not able to move this needle in this direction. Actually, it's supposed to move in this direction, but we are not able to observe that behavior here. So in order to see that, in order to get some experience on that, so we have to change our setup a little bit. We will use this one. So the current will be flowing through this copper wire, and then we will be using this magnetic compass. We'll keep it like this, and then let us see the deflection of this magnetic compass. Let me pass the current from this direction, and let us see the deflection. So let me connect this side as negative terminal. So let me connect this as negative terminal, and let me connect. Let's observe the behavior of the deflection. So let me put it a little near. Let us see. We observe that the deflection is 180 degree. Why the deflection was 180 degree? Because the current is flowing. So if flowing from this direction to this direction, so according to right hand thumbs rule, I have to hold it like this. So when I hold it like this is a north pole and the tips of the magnetic compass. So first it experiences a repulsive force. Because of that, this north direction should be coming to this, should be in this position. That is why it rotates 180 degree and it deflects 180 degree. So let me do the experiment once again. So if I keep it like this, so it's 180 degree. Now if we move away from this wire, how will be the deflection? Let us try to find at this point. So let me see. It deflects, but the deflection is not exactly even 90 degree. So it means that let us keep it somewhere here and let us see the deflection. Let us see the deflection here. It deflects, but it is not, the deflection is not as strong as when I keep near the wire. There was a deflection of 180 degree here. There was a deflection of nearly 90 degree, and even here it was less than 90 degrees. So let us see how much is the deflection for this. So it's less than 90 degree. But if I keep it here, let us see the deflection. It is 180 degree. So it means that the magnetic field varies based on the position from the current carrying conductor. If it is near to the current carrying conductor, the magnetic field is strong. If we move away from the current carrying conductor, the magnetic field reduce. So from that we can derive, or we can conclude that the magnetic field is inversely proportional to the distance from the current carrying conductor. And second thing, another thing that we can see in this setup also, if we change the amount of current flowing through this conductor, we can check the magnetic field strength. So first let me reduce the the voltage so that the current flowing through this copper wire is less. So let me connect this one. It has a deflection, and I don't have the proper instrument to measure the exact current flowing through this, so it has a deflection with this voltage. So let me increase the voltage at this point. I have increased the voltage, so obviously the current will be more. So let me see. Now it is more, the deflection is more. So if I reduce the current, the deflection is less. If I increase the current, the deflection is more. Then it means that the magnetic field is again directly proportional to the current flowing through this copper wire. So from the experiment which we have done, it is clear that the current carrying conductor has a magnetic field around it. Right now we did the experiment for the current carrying conductor for a straight line. We can find out the magnetic field for this type of wire. This is in the form of coil, or a single circle in this form. So what will be the behavior of the magnetic field? So that we will do in the next video. So in this current setup, I can keep one more magnet, and we can see what will be the behavior of the deflection. I have mentioned that the magnetic field is concentric circle. So in this case, let us see how the magnetic compass deflect. This will deflect 180 degree, and this should not change. This should not deflect, because if you applied right hand thumbs rule, the magnetic compass is already in the direction of the magnetic field. So let me connect the wire, and let us see. When I connect it, it is not moving because this compass is not very sensitive, as so this is more sensitive. So let me see once again. So this is rotating, but this is not rotating. So let us change this one here. So let me see this one, and if when I touch it, it is not moving much. This magnetic compass is not moving, because if you apply right hand thumbs rule, the current is flowing through this. So if you apply right hand thumbs rule, this is already in the direction of the magnetic field. But if I keep it on this side, it will be 180 degree. But if I keep on this side, it is not deflecting. Likewise, if I keep it here, let us see whether does it deflect. Here also it doesn't deflect much, because is it if you do like this right hand thumbs rule, this is already in the direction of the magnetic field. But if I keep it on this side, let us see. Actually, it should turn 180 degree, but it is not turning. Maybe the magnetic compass needle is already disturbed. Or let me see once again. It is not, or is it because of? Yes, let me see once again. Let me it is deflecting, but it's not able to exactly turn 180 degree. This has to turn 180 degree, but it's not turning 180 degree. If you like my video, please share your comments, and if you want me to do some other setup with respect to this experiment, please do let me know in the comment section. And thanks for watching. In the next video, let us try to find out the magnetic field of this coil, and then of this ring type. Right now we have analyzed only for a current carrying conductor for a straight wire. Thank you for watching once again.